Good morning, everyone, or good afternoon, depending on your time zone. I'm Federico Chiariotti, and today I'm substituting for my colleague, Deshpande, the first author of the paper, and of course, we did along with Professor Andrea Zanella. The paper is entitled SMURF, Reliable Multipath Routing for FANETS, and it is about, of course, flying ad hoc networks, or FANETS. Flying ad hoc networks are networks of unmanned aerial vehicles, UAVs, which you might know as drones. They are used for tracking and monitoring operations, often in remote areas which are hard to reach for ground-based units. And thanks to the lower cost and commercialization of new models of drones over the last few years, they have become a topic of high interest from both the research community and the industry for civilian as well as military applications. So, being a network, FANETS require communications between UAVs, so from UAV to UAV, and to the ground. Usually there is a ground control station, which is depicted in the figure, and of course, the wireless transmission technologies do not always have a very large range, so depending on the application, FANETS might require multiple hops to reach some of the farther drones. And this is, of course, being a routing paper, is the scenario that we are in. And the other interesting feature is the highly dynamic topology. Since drones need to accomplish their mission and move fast in the sky, often they go in and out of each other's transmission range, changing the logical topology of the network. So the previous works on routing in FANETS were usually based on the position of the drones, which determined the existence of the links. So position is usually determined by GPS coordinates, along with a set of other sensors such as accelerometers or gyroscopes. And previous works usually updated former mobile ad hoc network protocols such as AODV and OLSR. Of course, these updates did not consider uncertain information regarding the position. So what happens if the drones are really do not have a precise estimate of their position? And being protocols that are acted distributedly, of course, neighbors' positions need to be tracked by each UAV. So each UAV needs to take care of tracking its neighbors' positions and determining the best routes. Further expansions of the work in the literature considered uncertain information about the position, but they did only consider each link separately. And this is a problem, and we're going to see why. So our work is called SMURF, or Stochastic Multipath Routing in FANETS, and it uses a multivariate Gaussian node position model, which is consistent with Kalman tracking, which is the standard in tracking systems. But the important thing is that it is centralized. So it uses the software-defined networking paradigm, or SDN, to make ground control track the UAVs and determine the routes. So the ground control station acts as an SDN controller, and it calculates the best routes and it disseminates them to the various nodes. This simplifies the system a lot, especially if we want to use a separate technology to track the UAV's position. For example, we might use a high-capacity technology such as millimeter wave to transmit the actual data from the drones, the video, for example, that they record with their cameras, and a long-range technology such as LoRaWAN to disseminate updates about their position. This is to ensure the robustness of the tracking updates. And of course, having centralized routing simplifies the system a lot because the drones only need to have LoRaWAN transmitters and not receivers. So we, of course, explicitly compute the link existence probability in a joint way. So let us consider the scenario here in the slide. We have 3 drones that are in a row, one after the other, and the one on the left wants to send data to the one on the right. So in the first scenario, the one above, the drone in the middle is close to the first one. So the first link in the route has a high probability of existence because the two drones are close. So it's highly unlikely that that the drone in the middle will move away and the link will disappear. But the second link has low probability of existence, of course, because the distance is much larger. And in the system below, the situation is reversed. So link 1 has a low probability, but link 2 has a high probability. Of course, we can set up the system so that these two scenarios have the same overall probability of successfully delivering the packet, but routing algorithms that do not consider multiple links will see them as very different. So we compute the joint link existence probability. We do it for just two links, even though there are correlation even with multiple links, because it is not an unrealistic approximation. The simulation's results show that it's pretty similar, and of course it is much simpler to compute. I'm leaving the equations out of this presentation, but if you're interested, you can ask about them to Anai or go to the paper to read them. So once we have the link existence probability for couples of links, we can create a spanning tree. So here in the figure, you can see the spanning tree from node 1 on the upper right using the logarithm of the existence probability as a cost. So a standard spanning tree. Then the controller can disseminate the routing updates. So if there are any changes in the routes, it can send SDN messages to the drones to update their routing tables. One other thing that we can do is getting backup routes. So reliability of FANETS is pretty low because of the highly dynamic topology, even when we have the optimal route, which we get from the spanning tree. So what we can do is we can multicast to get additional reliability. So packets are sent through here in the example, if the drone on the left wants to send a packet to the drone on the lower right, it sends a packet to the first drone in the route, which then sends two packets, one to the upper drone and one to the drone below. So of course, this can improve the reliability. And we determine the backup routes to minimize the failure probability. So it is not the second best route in general. It is the route that is has the highest probability of existence if the first route fails. So it should share as few links as possible with the first route, provided that it has a high probability of existence. So there is this trade-off between having a high probability of existence in general and having orthogonal failure modes to the first route. So in our simulations, we considered a scenario like the one I described a few minutes earlier. So we have a low capacity, high range technology to transmit position updates, which the control center receives, and the control center can then decide the routes for the high capacity, low range technology, which is in our case millimeter wave. We did a very simple simulation, so we did not really consider aspects of millimeter wave, just a transmission range of 100 meters, which is realistic for air-to-air links. So with these updates, we can compute the routes. And here is how we do. So we considered MPGR, which is a routing algorithm from the literature, which didn't really do very well in the scenario we considered. A simple distance-based approximation, so we take the mean of the distribution and compute routing over that. Of course, it did a little bit better, but also not very well. And then we use SMURF. As you can see, even with just one path, it is very good. And additional paths have diminishing returns. So going from 1 to 2 and from 2 to 3 gives a perceivable difference. But going from 3 to 5 is not really, does not really change much. And of course, the number of routes should be minimized to preserve efficiency. We can also see oracle routing, which is the perfect, essentially, routing, which does not always have 100% reliability because the network might not be connected. So even if we know everything about the graph, there might not be a way to transmit the data. And as you can see, we do almost as well as oracle routing. So it is a very good result. Here we see the mean reliability as a function of the density of the nodes. And of course, a higher density per area, as we plotted on the x-axis, should lead to better routing. However, this is not always the case with distance-based routing, which, as long as there is, of course, a minimum density, does not really change that much. While in SMURF, it makes a lot of difference. And this is because with a higher density, there is a high probability of finding a next hop that has a very low uncertainty. So it is a very safe hop, which is, of course, the one that SMURF will choose. In the worst case, here we take the 25th percentile of the networks that we analyze. You can see that the benefits are even better, because the worst case of a scenario with a high density is still connected. So SMURF can exploit those connections to improve its performance even more, while the distance-based algorithm does not really fare well. Finally, we did a sensitivity analysis. So we tried to see what happened if we intentionally underestimated the variance of the multivariate Gaussians that represented the positions of the drones, or overestimated. And the result is essentially the same. So for even a 20% change in the variance with respect to the actual variance, it still works. So to conclude, we considered explicitly link correlations and uncertainty and put everything together in a centralized SDN routing protocols, which is consistent with the tracking framework. Of course, there's another paper of ours that develops the tracking framework, so I would advise you to check it out. And we perform multicast for additional reliability. In future work, we can consider a more realistic channel model with obstacles, and consider the stability of routes, so the existence over time, not only over one step, but over multiple steps of the tracking. And this, of course, opens the way to learning-based routing, which is the thing that we're looking at right now. Thank you, and of course, Anai is going to be here